Welcome to Physics 2. This is a crash course designed to help you understand the key concepts quickly and clearly. We focus on what really matters for your exams. Simple explanations, practical examples, and essential tips. Let's get started. Let's look at the roadmap for this Physics 2 crash course. We've organized the entire semester into 3 logical blocks. We start with electrostatics. This is the stationary phase where we look at charges that aren't moving yet. We'll master the force between particles and learn how to use Gauss's law, which is a total lifesaver for finding electric fields without doing messy calculus. In the second block, things start moving. We'll look at how we store that electrical energy in capacitors, and then dive into actual DC circuits. This is where you'll learn Kirchhoff's laws, which are the bread and butter of circuit analysis. Finally, we hit the connection between electricity and magnetism. We'll explore how moving charges create magnetic fields, and how, conversely, a changing magnetic field can actually induce or create electricity. This last part is essentially how every power plant on Earth works. Exam tip. Most students struggle with the transition from electric fields to magnetic fields. Pay close attention to the symmetry between Gauss's law and Ampere's law. They are 2 sides of the same coin. Chapter 1. Electric charge and Coulomb's law. In this chapter, we will study the fundamentals of electric charge and Coulomb's law. First, we review the basic properties of electric charge, including quantization and conservation. Then, we move to Coulomb's law and the key constants used in electrostatics. Next, we learn how to apply the superposition principle and analyze forces using vector addition. We will also cover equilibrium conditions and optimization of forces in different problems. Finally, we will solve the most important exam questions from this chapter. Let's get started. In this lesson, we introduce electric charge and Coulomb's law. Electric charge is a fundamental property of matter. One key idea is quantization. Charge exists in discrete amounts, given by Q equals NE. Another important principle is conservation of charge. The total charge in an isolated system remains constant. Now, let's move to Coulomb's law. Coulomb's law is given by F equals K times the absolute value of Q1, Q2 divided by R squared. In equation form, F equals K times Q1, Q2 over R squared. Here, F is the force between the charges. K is a constant, approximately equal to 9 times 10 to the power of 9. And R is the distance between the 2 charges. This means the force increases with larger charges and decreases rapidly as the distance increases. Finally, remember that electric force is a vector. Like charges repel and unlike charges attract. These concepts are essential for solving exam problems. Now, let's introduce the superposition principle. When multiple charges are present, the total force on a charge is the vector sum of all individual forces acting on it. This means we add forces vectorially, not just algebraically. Now, let's look at this example. We want to find the net force acting on charge Q1. So we write F net equals F12 plus F13 plus F14. Now, let's analyze each force. Charges Q1, Q2, and Q3 are all positive, so they repel each other. The force F12 pushes Q1 downward, and the force F13 pushes Q1 to the right. Now, charge Q4 is negative, so it attracts Q1. Therefore, F14 is directed toward Q4, which is down and to the right. Finally, we combine all these forces as vectors to find the net force. Before solving problems, remember a few important exam tips. Always convert units correctly, especially microcoulombs to coulombs and centimeters to meters. Use only magnitudes in the formula and determine the direction separately. Also, keep key constants in mind for quick calculations. Now, let's express vectors using I and J notation. Any force vector can be written as F equals F times I plus Fyj. Here, I represents the x direction and J represents the y direction. To find the components, we use cosine and sine. Fx equals F cosine theta and Fy equals F sine theta. Here is an easy way to remember this. The axis that the angle touches uses cosine. The other axis uses sine. Now don't forget the signs. Right is positive I, left is negative I. Up is positive J, and down is negative J. So finally, we can write the vector as F equals F cosine theta I plus F sine theta J. This form makes vector addition much easier in problems. Let's solve a complete exam problem. 4-point charges are arranged as shown. Q1 is plus 2 microcoulombs. Q2 is plus 3 microcoulombs. Q3 is plus 4 microcoulombs. And Q4 is minus 5 microcoulombs. All at the same distance, R equals 0.2 meters from Q1, and theta equals 45 degrees. We are asked to find three things. 1. The net force in vector form. 2. The magnitude of the force. And 3. The angle. Now, let's solve this step by step. First, using Coulomb's law, we substitute the values into the formula. This gives us F12 equals 1.35 newtons. F13 equals 1.8 newtons. And F14 equals 2.25 newtons. Next, we determine the direction of each force. Now, we convert the forces into I and J components. F12 becomes minus 1.35 J. F13 becomes plus 1.8 I. For F14, using cosine and sine at 45 degrees, we get 1.59 I minus 1.59 J. Now we add all components. The X component is 3.39 and the Y component is minus 2.94. Finally, the net force is written as 3.39 I minus 2.94 J newtons. Now we find the magnitude. Taking the square root of the sum of squares, we get 4.48 newtons. Finally, we calculate the angle. Using the tangent inverse, we get approximately 41 degrees. Since the y component is negative, the direction is below the positive x-axis. This completes the solution. Now let's solve another important exam type problem. 2-point charges are placed at a distance of 50 centimeters. Q1 is plus 4 microcoulombs and Q2 is plus 9 microcoulombs. We are asked to find the position where a third charge experiences zero net force. Before solving, remember this key idea. For like charges, the equilibrium point lies between them, and it is closer to the smaller charge. Now let's solve step by step. In this problem, both charges are positive, so they are like charges, and the equilibrium point lies between them. Let the distance from Q1 be x. Then the distance from Q2 is 50 minus x. For equilibrium, the forces must be equal. So we equate the magnitudes using Coulomb's law. After simplifying, we get 4 over x squared equals 9 over 50 minus x squared. Taking the square root, we get 2 over x equals 3 over 50 minus x. Solving this equation gives x equals 20 centimeters. So, the equilibrium point is 20 centimeters from Q1. And that wraps up part 1 of our course. Great job for staying with me until the end. In the next part, we'll continue with more important concepts and exam-focused examples. So don't forget to like the video and subscribe to the channel to stay updated with the next lessons. See you in the next class, everyone.